All right, so lesson 4C is going to be on something called local linearity. So local linearity is when when you know information about a tangent line and you know some information about a function, but you are unable to find the specific value of a function at a specific point. So you use the tangent line close to that point to estimate the value of the function at that point. So for example, if if I have a value on a graph that I'm trying to find. So for example, this point right here, we're going to call this point the point where x is a, and then the output, of course, would be f of a. So we're trying to figure out what f of a is, but we don't know what that is. But what we do know is we know the equation of a tangent line of a point really close to A. So this line right here is a tangent line to a graph at a point really close to A. And what we're going to do is we're going to use the value at A on this line to estimate what the output is at A. So it's going to be a number close to it, but it won't be the exact same number because these 2 points, I'm going to make one of them blue. So the blue point on the line and the purple point on the actual function, while they're close together, they aren't exactly the same. So, but you're able to take a tangent line that's really close to that point and find the value at that specific value on that line. And that'll be a close estimate for what the value is of the function on the actual graph. Now, when you're looking at a graph that is concave up, okay, which means the slopes of the graph are increasing. And the second derivative is positive. So if something is concave up, the second derivative is positive. It's greater than 0. And the slopes are increasing. If that is the case, then this estimate that you're getting is going to be an underestimate because the tangent line is actually below the graph. So if it is concave up, where you're finding the estimate, if those slopes are increasing, okay, the slopes of the tangent lines are increasing, then your local linearity estimate or approximation is going to be an underestimate. Now, when you have a graph that is concave down, so if you're trying to do the same thing on a graph that's concave down, so I have this point here, A, and I'm trying to find the output, and I know the equation of the tangent line very close to it. Okay, so I'm able to get the value on the tangent line right here. Now that, if it's concave down, meaning that the second derivative is negative and the slopes are decreasing, then it's going to be an overestimate because the line is above the graph. Okay, so this one would be an underestimate. And this would be an overestimate. Okay, so depending on how the graph is shaped, your estimation or approximation that you find using this local linearity is going to either be an underestimate or an overestimate. So here's like a little chart that tells us the same thing. So we have this graph here. We have this section of the graph that is concave down. And we have this section of the graph that is concave up. So on the section of the graph that is concave down, where the slopes are going to be decreasing, the second derivative is going to be negative, and we're going to have an overestimate. On the section of the graph where it is concave up, where the slopes are increasing. The second derivative would be positive. We have an underestimate. So again, depending on how the graph is shaped, that is going to tell us whether our local linear approximation is going to be a overestimate or an underestimate. So remember, concave up, underestimate. Concave down, overestimate. Because if it's opening downward, okay, the line's going to be on top of the graph. It's going to be above the graph. If it's opening upward, the tangent line is going to be underneath the graph. So that's kind of what you need to think. If it's opening down, tangent line is on top. Okay, it's above. If we're concave down, so overestimate. If we're concave up, the tangent line is going to be underneath the graph. So concave up, we're under, and it's going to be an underestimate. Okay, so you got to keep those straight because you're going to be asked whether they're underestimates or overestimates. So let's go ahead and look at an example. So f is concave up on its domain with f of 4 equal to 5 and f prime of 4 equal to 3. What is the estimate for f of 3.8 using the local linear approximation for f at x equals 4? So we know what's happening at f of 4. We know that f of 4 has an output of 5. And we're asked to use that to estimate the value of the function at 3.8. So it's a number very close to 4. Now, when we are trying to figure this out, I'm going to show you two different ways. I know y'all aren't very comfortable with point slope, but there are going to be some answer choices that use point slope form. So I am going to show you some of these using point slope form just to get you a little bit more comfortable with it. Now, point slope form is just a variation of slope intercept form where they pretty much like don't simplify it almost. And it's weird, like the x, like when you plug the numbers in, the x and y are there and the slope is there, but you don't like actually work it out and try to get it in y equals mx plus b form. So point slope form, I'm going to write this down for you. So we have point slope form, and I'm going to put it more in like the derivative format. So point slope form is y minus f of a. Now f of a is just the y output from like the function. And then f prime of a, that's actually the slope, times x minus a. Now I'm going to like point out what all these things are. So right here, this is just the y value from the point. This is just the slope at the point. And this is the x value of the point. Okay, so this is x. The 4 is the x. The 5 is the f of 4, or the y. And this is the slope. So this is f prime of 4, but it's also m. So I'm going to use this formula sum just to get you comfortable with it. I'm also going to use slope intercept form sum, just so we can see both of them because you don't know what you're going to see on the exam. So it says, what is the estimate for 3.8 using the local linear approximation for f at x equals 4? So I'm going to go ahead and plug in the values into the point slope form formula, and then I'm going to use that formula to estimate f of 3.8. So my values that I'm looking at in this problem are f of 4 equals 5 and f prime of 4 equals 3. So I'm going to set up the point slope form using that information. So I'm going to have y minus f of 4 equals f prime of 4 times x minus 4. And then I'm going to go ahead and put in y minus 5 because that's what f of 4 is. So that is the y value of the point. Okay, so the point was 4, 5, the point on the original function. That is my x, that is my y. So this is the y from the point. Then I'm going to find the slope of the tangent line, which is the derivative at that point. So that's going to be 3 times x minus 4. And this is just the y value from the function. And this is just the x value from the function. And this is just the slope of that tangent line, or the derivative at that point. So this equation that I've just crafted here, this is the equation of the tangent line to f at 4. So if I were to graph f, I don't know what f looks like. It's concave up. So I'll go ahead and draw a concave up graph. So let's just say 4 is right here. So this is x equals 4. This equation would be the equation of this, well, it would be the positive one, because it does have a slope of positive 3. So this would be the equation of the tangent line at that specific point. Again, it's probably not completely accurate because that really doesn't have a slope of 3. But that's what we just found. Now, we are trying to find f of 3.8. So 3.8 is going to be just before 4, okay? So what we're going to use is we're actually going to find the value at 3.8 on the tangent line, and we're using that to estimate the value on the actual graph. So what I'm going to do is I'm going to plug 3.8 in for x and then evaluate it. So I'm going to have y minus 5 equals 3 times 3.8 minus 4. And then I'm going to simplify that down. Oops, not 3. I'm going to multiply that together. So I get negative 0.6. And I'm going to add 5. So I'll get 4.4. So now that's not the actual value at x equals 4, but I'm using it to estimate the value at x equals 4. Now the value at x equals 4 is 5. So at 4 we have 4, 5. So we're a little bit below that, so we're at 4.4. So that's my estimation there. 4.4. I wouldn't need the y equals, it's just the 4.4. Now the second question says, is it an underestimate or underestimate or an overestimate? Well, from the picture you can see that the line is below the actual graph. So it's going to be an underestimate. Now, the actual explanation there is that the graph is concave up, so the tangent line is underneath the graph. And we know it's concave up because it told us that. So the function f of x is concave up. So the tangent line is below the graph. So that's the description there of why that is so. Now for the next one, I'm going to use point slope form. I mean, not point slope form. I'm going to use slope intercept form. And then probably for the rest, I'm going to use point slope form just because that's the one you're the least familiar with. Point slope form isn't bad for this one because you're just plugging something in. So it's honestly a little bit easier probably than slope intercept form for these problems. It's just the one you're not as familiar with. All right, so now we have a function. We actually have the function this time. So the function f of x equals 5x minus 2x cubed minus 2. And it says it is concave down at x equals 1. Then we're going to find the estimate for f of 1.1 using local linear approximation for f at x equals 1. And then we're going to see is it an underestimate or an overestimate. Now, could we just find f of 1.1? Yes. Now, doing it by hand, it would be a little bit more difficult than using local linear approximation. But I know we could actually find it because we do have the actual function f, but they're asking us to use linear approximation to find it. So that's what we're going to do. So first we're going to find the tangent line of f at x equals 1. Now, I don't know my output, and I need to know my output, and I also need to know my derivative so I can find my slope. So when you're finding the tangent line, those are the things you need. You need the point. So you need the input and the output. We only have the x value. We need to plug it in to find the y. And then we also need to find the slope of the tangent line, which comes from finding the derivative and then plugging the x value into the derivative. So I'm going to do both of those things. First, I'm going to plug just 1 into the function to figure out what f of 1 is. So f of 1 equals 5 times 1 minus 2 times 1 cubed, but that's still just 1, minus 2. 5 minus 2 is 3, and 3 minus 2 is going to be 1. So my point is 1, 1. Now, I'm going to find the derivative. So I'm going to find f prime of x, which is going to be 5 minus 6x squared. And I'm going to plug 1 into that now. So it's going to be 5 minus 6, or it's going to be negative 1. So my slope of my tangent line is negative 1. My x value is 1, and my y value is also 1. So I'm going to go ahead and create this equation. I'm going to use slope-intercept form this time instead of point-slope form, but we could also use point-slope form. I'm just going to kind of change it up and do some of both. So I have y equals negative 1x plus b. That negative 1 came from the slope of the tangent line, which comes from the derivative. Then I'm going to go ahead and plug in my x and y, which are both 1. So I'll end up with 1 equals negative 1 times 1 plus b. 1 equals negative 1 plus b. So b is going to be 2. So that means the equation of my tangent line is y equals negative 1x plus 2. So that is the equation of the tangent line. Now, it says what is the estimate for f of 1.1 using the local linear approximation for f at x equals 1. So this tangent line is what provides the local linear approximation for f. Now, 1.1 is close to 1, so I'm going to plug 1.1 into my tangent line for x, and that's going to give me an approximation of what f of 1.1 would be. It's not going to be exact, but it's going to be close. So I'm going to go ahead and plug that in. So I'll have y equals negative 1, but instead of x, I'm going to plug in 1.1 plus 2. So I get y equals negative 1.1 plus 2, which means y is going to equal 0.9. So 0.9 is the estimate for f of 1.1. Now, is this an underestimate or an overestimate? So we need to look at the concavity of the original function. The original function is concave down, which means it is going to be an overestimate because the tangent line was actually above the graph. So it's going to be an overestimate. Anytime it's concave down, it is an overestimate. The graph is concave down. Therefore, the tangent line is above the function or the graph of the function. Now for this one, I'm going to actually graph it just so you can kind of see how close we are. So I'm going to go ahead and graph the original function, and I'm going to graph the tangent line, and then I'm going to see where 0.9 is, like, or how close it is to actually f of 1.1. So I'm actually going to graph this. So what I have graphed here is I have the original function, and I have the point on the function that we found the tangent line to. So here's our tangent line. So that's the tangent line we found to that function at that particular point. You do see that at that particular point, that portion of the function is concave down. So you see that the tangent line is above the graph. Now I'm going to turn the tangent line, or I'm going to turn the point off and keep the tangent line up there. So I'm going to turn that point off. And now I'm going to talk about the points that we with the point we used the estimation and the actual point that's on the graph. So this is the point that is on the tangent line that we use to estimate the actual point on the graph. So I'm going to turn the point on the graph on so you can see it. And you'll see that that point is pretty much, when I turn it off and turn it back on, like it's pretty much right on top of our estimation point. So it is a pretty decent estimation. You are going to notice, though, if you look at the actual points, the point on the actual line is 0.838. So it is a little bit, the point on the actual graph is 0.838. Our estimation was 0.9, so it was an overestimate. We were too high. And you're going to notice the further you zoom in, you will start to see the difference between the point on the line and the point on the graph. So while they are close together, there is a little bit of a difference there. So the tangent lines do give us a close estimate, but it's still going to be off a little bit. The steeper the slope is, like negatively or positively, the more off it's going to be. So if this was like a wider curve, then the estimation would be a little bit closer. But it is an overestimate, so it is a little bit higher than the actual graph there. I just wanted to show you what it looked like and how that linear approximation or that local linearity, how using that does give you close to the graph, but it's not perfect, obviously. So example 3, it says, consider the differential equation dy over dx equals e to the y times 2x squared minus 5x. Let y equal f of x be the particular solution to the differential equation with the initial condition f of 2 equals 0. And then we're going to try to write an equation for the tangent line to the graph of f at the point 2, 0, and then we're going to use that tangent line to approximate f of 2.2. All right, so in this particular problem, I picked this one because it uses some language that we are going to dive into in later units, but I wanted to go ahead and talk a little bit about differential equation and particular solution and initial condition and what those terms mean. Just in case you come across them in any of like the progress checks or anything like that, you'll have an idea of what they're talking about, even though those particular units, we haven't gotten to them yet, that dive into what a differential equation is, what a particular solution is, and what an initial condition is. So a differential equation is a derivative of a function. So we know what a derivative is. Usually a differential equation, when we're looking at it, most of the time it's a derivative that was found by implicit differentiation. Now, when we refer to them as differential equations, a lot of times we're doing other things with them, which we're going to learn about later. But a differential equation essentially is a derivative. Okay, so dy over dx equals e to the y times 2x squared minus 5x. That is the derivative of a function. Now, they're saying that this is the derivative of f of x. So f of x is our original function. And we're saying that that is a particular function that would have this derivative. And that particular function that has this derivative has an initial condition of f of 2 equals 0. So that initial condition, f of 2 equals 0, represents an input and an output on the original graph. So on the original graph, f of x, 2, 0 is a point that is on that graph. Now, what you need to understand is when you take the derivative of something, the thing that disappears and is not a part of the derivative is any constants that were on the original function. So I'm going to kind of make this more basic. If I have f of x equals 2x plus 6 and g of x equals 2x plus 10, the derivative of both of these is 2, right? So if I were just looking at the derivatives, I wouldn't be able to tell what the actual initial function was. But an initial condition actually gives you more information about the function because it ties in a particular form of that original function. So if I knew that f of 0 equals 6 on the original function, then I would automatically know that it would be this one. But if I knew that g of 0 equals 10 on the original function, then I would know it's this function. So an initial condition gives you more information about the original function. Later on, when we start doing something called integration, we're going to take a derivative and we're going to work backwards to the original function. And we're only going to be able to find the exact original function if we have an initial condition. So that's just kind of like a little bit of a preview of what's coming next. But I wanted to go ahead and show you a problem like that, just in case it shows up, like I said, in progress checks or in homework or something like that. I'll probably refrain from using this language on the test, just because we haven't gotten to those particular units yet, but you might come across it in some other problems. So I wanted to go ahead and introduce those concepts to you and just let you know that they are just saying the derivative and a point on the original graph. That's really all those terms mean. So let's go ahead and dive into this problem. So I need to first, I know a point that's on the original graph, so 2, 0 is my point, but I do need to find the slope on the original graph. So I'm going to use the differential equation or the derivative to find the slope of the tangent line. So I'm going to take that dy dx and I'm going to plug in 2 for x and 0 for y, which is going to be nice because when I plug in 0 for y, then that e term is going to turn to 1 for me. So that helps out a lot. So I'm going to have 2 times 2 squared minus 5 times 2. So e to the 0 is just going to be 1. So that's really not going to do anything for me as far as the multiplication goes. Then I'm going to do 2 times 2 squared, which is going to be 2 times 4, and that'll be 8. And then 5 times 2 is 10. 8 minus 10 is going to be negative 2. So negative 2 is actually the slope of my original, the tangent line on that original function at that particular point. So this is my slope. So this is the slope of the tangent line. I'm going to do this one in point slope form, just so we can see it. Now, when you're doing point slope form, the slope of the tangent line goes right in front of that parentheses with the x's in it. So that negative 2 is going to go right here. On this side, I'm going to do y minus the y value from the point. So it'll be y minus 0. And then in the other parentheses, I'm going to do x minus 2. So that's how you set up point slope form. All right, so now I'm going to simplify this down, just getting rid of that 0. So I'll have y equals negative 2 times x minus 2. I could actually distribute this out and I could get a slope-intercept form problem and have it in slope-intercept form, but I'm just going to leave it like it is for now. But what is interesting to me is the y-intercept is going to be 4. And if you were to actually go and do it in slope-intercept form, I would plug in 0 here, negative 2 times 2 here. So you would see that b is going to be negative 4. I mean 4, because you would move it over, so it would turn into positive 4. So that's kind of interesting that you see that it is the same thing. All right, so I'm going to go ahead and plug in 2.2 in for my x value to do my linear or tangent line approximation. So I'm going to do y equals negative 2 times 2.2 minus 2. So y equals negative 2 times 0.2, which will be y equals negative 0.4. So negative 0.4 would be the approximation at f of 2.2 on that original function. All right, so example 4. Example 4 is more of an open-ended question, very much a free response style question. And example 4, I'm going to go ahead and kind of give you like a little hint here, is going to be very close or similar to example or our FRQ for Unit 4. So we are going to do an FRQ for Unit 4 next week, towards the end of the week, probably Thursday. I'm planning on our test being on Friday of next week for Unit 4. But this problem and your FRQ for Unit 4 have a lot of similarities. And what's interesting about this FRQ is it ties in a lot of stuff from Unit 2 and brings it back and applies this local linearity kind of to it as well. And also kind of talking about the second derivative and explaining what the second derivative means. So, example 4 says the depth of snow in a field is given by the twice differentiable function s for 0 less than or equal to t less than or equal to 12, where S of t is measured in centimeters and time, t is measured in hours. Values of S prime of t, the derivative of S, at selected values of time, t, are shown in the table below. I know it says above, but it's below. It is known that the graph of S is concave down for 0 less than or equal to t less than or equal to 12. So if S is concave down, then we can see that like we'll be able to tell something about the local linearity at the end. So that's important. Also, that is twice differentiable. That's important as well because that helps us know that the function, the original function, and the derivative function are both continuous. Because if you can take the derivative a second time, you can only take the derivative a second time if it's twice differentiable on that particular interval. And that is continuous on that particular interval, the first derivative is. All right, so it says use the data in the table to approximate S double prime of t, or of 10, sorry. Show the computations that lead to your answer. Using correct units, explain the meaning of S double prime of t. I keep saying t is 10, of 10, in the context of the problem. So I want to go ahead and just kind of talk about this table right here. So the original function S is just the depth of snow at certain hours. So hour 1 or hour 0, hour 1, hour 2, and so on all the way up to 12. So that's the original function. The original function is just the depth of snow. The derivative function is the rate the snowfall is changing, or the rate the depth is changing, not the snowfall. So this first derivative, this table right here, is the rate the depth of snow is changing. So, for example, at hour 4, the derivative is 2.0. That means at hour 4, the snow is falling at a rate of 2 centimeters per hour, okay, at hour 4. So when you look at a function that's a derivative, you already know that that is a rate of change. Now, we're going to go ahead and use the data in the table to approximate the second derivative. So the derivative of the derivative at t equals 10. Now, 10 is not in our table, okay? But since the table is the first derivative, the table has values of the first derivative, if we approximate the second derivative by using values around where 10 would be, then we can just use that difference quotient to approximate the second derivative. Just like in previous unit, in unit 2, we used the table of an original function to approximate the derivative of a function or the slope of a tangent line at a particular point. So we're doing the same thing here. We're just finding the second derivative because what's in the table is the first derivative. So I'm going to use 9 and 12, those two columns, to find or to estimate the second derivative at 10. So I'm going to go ahead and set up my difference quotient. So S double prime of 10 is going to be S prime of 12 minus S prime of 9 over 12 minus 9. Now, S prime of 12 is 1.3. S prime of 9 is 1.6. And we're doing 12 minus 9. So we're going to get negative 0.3 over 3, which is negative 0.1. Now, this is the second derivative. So if we're looking at the first derivative being the rate the depth of snow is changing, okay, so this negative 0.1 means that the rate the depth is changing is decreasing 0.1 centimeters per hour every hour. So essentially what that is saying is the snow is still falling, but now it's falling slower than it was before because the rate of change of the depth is decreasing. So it's not changing as quickly as it was before. So I'm going to kind of write that out in words. So So at hour 10, or sometimes I'll say at the end of hour 10, because technically t equals 10 is after hour 10, right before hour 11 starts. So at hour 10 or the end of hour 10, however you want to say it, you'll see it both ways, kind of, in a lot of problems. So at hour 10, the rate of the depth of snow is decreasing 0.1 centimeters per hour per hour. And I'm going to put that up here, centimeters per hour or per hour squared. So when you're finding a second derivative, it is describing the change of the rate of change. So at hour 10, the rate of the depth of snow is changing. Specifically, it is decreasing 0.1 centimeters per hour. So at hour 10, it has negatively snowed, not negatively snowed, but the rate at which it's snowing has decreased. So it's not snowing as fast, but it is still snowing. Just the rate is decreased, not the amount of snow. Obviously, the amount of snow is not going to decrease until it warms up and melts, right? Your depth keeps increasing, but since the second derivative is negative, the rate at which it's increasing is decreasing, if that makes sense. So, B, is there a time t for 0 less than or equal to 12, t less than or equal to 12, at which the depth of snow is changing at a rate of 1.5 centimeters per hour? Justify your answer. Wow, this really, to me, looks like an IVT problem, okay, because we have a table, we have values in the table, and it's specifically asking me, is there a place at which the depth of snow is changing at a rate of 1.5 centimeters per hour? That is what is in our table. It's the rate the depth of snow is changing. And we can look at our table and see if 1.5 would be in that table, because we already know that S prime of t is continuous. And since it is continuous, we can apply the IVT, the intermediate value theorem, if that value is between other values in our graph. So when I look at my table. When I look at my table, I see that 1.5 specifically will be in between 1.6 and 1.3. So on the interval, so yes, on the interval, 9 less than or equal to 12, or sorry, t, gotta put t in the middle. Nine less than or equal to t less than or equal to 12 is specifically when it's going to happen. There will be a value t where S prime of t equals 1.5 by the IVT. Now, I could establish that S prime of 9 is 1.6 and S prime of 12 is 1.3 and 1.5 is between 1.6 and 1.3. I just don't have a lot of room to write that out. But definitely over-explain, okay, always. So S prime of t is continuous. That is important that you know it's continuous because it is differentiable. It doesn't specifically say it's continuous in the problem. It says it's differentiable in the problem, but that also means it's continuous. So yes, on the interval, 9 less than or equal to t less than or equal to 12. So that's where it happens on that specific interval. There will be a value t where S prime of t is 1.5 by the intermediate value theorem. Okay, so C, at time t equals 4. So at t equals 4, the depth of snow is 28 meters. Now, We didn't know that looking at our table because our table is only telling us how it's changing. It's not telling us specifically what the depth of snow is. But they're telling us at t equals 4, the depth of snow is 28, which means 4 and 28, I'm going to write this up here because I don't have a lot of space down there. 4 and 28 is a point on the original function. So this is a point on S of t because S of t is just talking about the depth of the snow. Use the tangent line to the graph of S at t equals 4 to approximate the depth of snow at time t equals 6. Is the approximation an underestimate or an overestimate of the actual depth of snow at time t equals 6? Well, we already know what kind of estimate it's going to be. This is concave down, which means the tangent line is on top of the graph because the graph is opening down. So it's going to be an overestimate. We already know that. So I'm going to highlight that. We know it's going to be an overestimate specifically because we know it's concave down. Now, let's go ahead and use the information they gave us to find our tangent line equation, and then we'll plug 6 into that to approximate the depth of snow at t equals 6. So first, at 4, our slope is going to be 2. That's from the table. The first derivative is the slope of the tangent line. So I'm going to do this one in point slope again. So I'm going to do y minus the y of the point, which is 28, equals the slope, which is 2, times x minus the x from the point, which is 4. So that's the point slope form of that equation. And now I'm going to plug 6 in for t. I guess I should have used t instead of x. So let me go ahead and change that to t. All right, so I'm going to go ahead and plug in 6 right here for that t value. So I'll get y minus 28 equals 2 times 6 minus 4. So I'll get y minus 28 equals 2 times 2, which is 4. And if I add 28, I get y equals 32. So 32 centimeters. That would be the estimate, but that would be an overestimate. Now, I guess instead of y, I should have used S2 to make it more fit in with the original problem. But now, I did do that in point slope form. That does not mean you couldn't do it in slope intercept form. You could put the slope in and then plug 4 and 28 in for x and y and solve for b, and then plug the value in just like we did in those other equations. I'm just trying to get y'all more comfortable with point slope form because it could pop up in some problems. All right, so now for examples 5 and 6. For number 5, we have a function f of x equals negative square root of 4 minus x. It's concave up on its domain. What is the estimate for f of 1.9 using the local linear approximation for f at x equals 2? Round to 3 decimal places. So it's telling us to use the tangent line at x equals 2 to estimate what's going on at 1.9. So for this one, it does say to round to 3 decimal places, which means we're going to have to use a calculator to figure that value out. We're not going to leave it with like messy square roots and all of that. We're going to have that decimal version of it. So I'm going to go ahead and set this one up, and then I'll put it in the calculator to figure out what it is. Now, for this particular problem, I do need additional information. So I only know the x value of the tangent line. I need to also know the output value, the y value. So I need to plug I need to plug 2 into f. So I need to figure out what f of 2 is, which will be negative square root of 4 minus 2, which would be negative square root of 2. So that is my y value. Just gonna write it a little bit better. Okay, so that's going to be my y value. That goes with my x value. So this is my y. Now I need to find also the slope of the tangent line. So I do need to find the derivative of that function. So I'm going to go ahead and rewrite f of x just to look a little bit better for finding the derivative. And now I'm going to go ahead and find the derivative. So f prime of x equals negative 1/2 times 4 minus x to the negative 1/2 times negative 1. And the reason I'm multiplying by negative 1 is because the derivative of 4 minus x is negative 1, because negative 1 is the number in front of the x. Now I'm going to go ahead and evaluate this at 2. I am going to rewrite it just a little bit to help me out. So I have negative 1 times 1/2, which will turn into a positive 1/2. And then I'm going to put that 4 minus x back under the square root on the bottom because it is a negative 1/2 is my exponent, which means it's on the bottom and underneath the square root. So then f prime of 2 is 1/2 times 1 over the square root of 4 minus 2. So I end up with 1 over 2 square roots of 2. So that's going to be my slope. So this is my m. Now I could use slope-intercept form and solve for b. With the messy numbers, I think I'm just going to use the point slope form, and then I'm going to put it into the calculator anyway, so it's going to end up kind of doing the work for me. So I'm going to go ahead and set that up. I'm going to have to use the space underneath b, but b is going to be a pretty easy question to answer anyway. So I'm going to do y minus the y value, which is negative square root of 2, so that's going to turn into a plus the square root of 2 equals the m, which is 1 over 2 square roots of 2 times x minus the x value, which is 2. And then I'm going to be evaluating this at 1.9 because that's what I'm doing my local linear approximation at. So I'm going to actually rewrite this first before I plug it in. I'm going to take that plus the square root of 2 and just stick it on the end as a minus square root of 2. That way when I plug it into Desmos, it'll evaluate nicely. So I'm going to have 1.9 minus 2 minus the square root of 2. So I'm going to put all of that into Desmos. And when I put that value into Desmos, I get negative 1.4495. And that's going to round up to negative 1.450. So negative 1.450 is going to be that solution. So y equals negative 1.450. And that is the local linear approximation using that tangent line. Now, it does ask if this is an underestimate or an overestimate. I'm just going to highlight which one it is. So it is concave up. So the graph is opening upwards, which means the tangent line is below the graph, which means it is going to be a underestimate. So concave up, under. Okay, UU, up, under. Okay, concave down is overestimate. So that's an underestimate, and the explanation would be that it's concave up. Therefore, the tangent line is underneath the graph. So any, of course, estimation using that tangent line is going to be below the actual graph. So it's going to be an underestimate. All right, now for example 6, it says f is concave down, and f of 3 equals negative 1, and f prime of 3 equals 2. What is the estimate for f of 3.2 using the local linear approximation for f at x equals 3? So I'm going to actually do slope-intercept form on this one just because the numbers are nice and I'm not having to plug them into the calculator or anything. So my point on my original graph is 3, negative 1. So that is my x and my y. And my slope is going to be 2 because that is f prime of 3. So I'm going to go ahead and plug that slope into my formula. And then I'm going to plug negative 1 in for y and 3 in for x. And I get 6, which means b is going to be negative 7. So my equation is y equals 2x minus 7. Now, I would get that same thing if I did point slope form. And I'm going to show that to you just so you can see that they are the same thing. They're just different forms of the same thing. So if I did y minus negative 1, that's my y value. I would end up adding it, equals 2, that's my slope, times x minus 3. Now, y plus 1 equals 2x minus 6. Then if I subtract 1, I will end up right back here. So you do get the same thing. Point slope form and slope intercept form do give you the same equations in the end. Now, it says, what is the estimate for f of 3.2 using local linear approximation for f at x equals 3? So we're going to use that tangent line and plug 3.2 into it. So y equals 2 times 3.2 minus 7. 2 times 3.2 is going to be y equals 6.4 minus 7. So y is going to be negative 0.6. Now, is this going to be an underestimate or an overestimate? It is concave down, which means the tangent line is on top of the graph. So it's going to be an overestimate, specifically because it's concave down, okay? When it's concave down, imagine a graph concave down. The tangent line is going to sit above the graph. So if you're estimating this point by using this point's higher than the graph. So it is an overestimate. All right, our last example is going to be using a table. So it says, example 7, selected values of a differentiable function f of x and its derivative f prime of x are in the table below. Write an equation of the tangent line to the graph of f at x equals 4. Use this line to approximate f of 3.8. So let's look at our table at 4. So at 4, our output, our y is -5. And our slope is going to be 6. So this is our x, this is our y, this is our slope. So we're going to go ahead and write our equation. So I'm going to have y equals 6x plus b. My y is -5. My x is 4. So -5 equals 24 plus b. And then if I move that to the other side, I'll get -29 equals b. So b equals -29. So my equation of my tangent line is 6x minus 29. And then I'm going to approximate 3.8. So I'm going to plug 3.8 into this function. So 6 times 3.8, 6 times 4 will be 24. But we're 1.2 less than that, so it'd be 22.8. Yes, 22.8. So y equals 22.8 minus 29. And that would be y equals -6.2. So that would be the approximation of f of 3.8 using the information from that table.